This is a video for AQA Further Pure Mathematics. This is Matrices section 2.4, Successive Transformations in Two Dimensions. Well, firstly, a reminder of the matrix transformations that we've met in earlier videos. So remember that all of these that we have here are reflections. It's possible to tell that these are reflections by considering the matrix determinant, and for all of these you'll see that the determinant of these matrices is equal to -1. So for a reflection, the determinant of the matrix is -1. The rotations we looked at, where we have a clockwise rotation is positive, and I beg your pardon, a clockwise rotation is negative, and an anti-clockwise rotation is positive. Here the determinant of the matrix M will be equal to +1. The other transformations we looked at were stretches and enlargements. Here, although we haven't actually considered it as yet, we'll see that the determinant of the matrix here will be equal to the area scale factor of the transformation. So for example, if we have an enlargement scale factor k, the area of the transformed figure will go up by a value of k squared. Now what I want to do now is to look at what happens if we follow one transformation by another. So for example, what if we take this triangle here and we transform it first of all by A, which is given by the matrix 1, 0, 0, -1, and then B, which is given by the matrix that's there. So what happens if we do A followed by B? Well, we could consider the triangle and do some matrix multiplication. However, an alternative way is to consider what each of these matrix transformations is. So A, we can see that this A is a reflection, and if you look at it carefully, you'll see that this is a reflection in the x-axis. And B is a rotation of plus 90 degrees, or in other words, an anti-clockwise rotation. So let's look at that happening on our diagram then. There's our triangle. If we first of all reflect it in the x-axis, it ends up at that position, and then we follow that with transformation B, which will rotate that triangle to this position. So we've got the reflection followed by the rotation. Now what we want to do is to consider what's the combined effect of those two. In other words, we want to go from the red one to the pink one, and we can see that that combined there is a reflection. So A followed by B produces a reflection in the line y is equal to x. And if we look at that from the point of view of our vectors I and j, they've ended up being reflected in this line. So I dashed will be up here and j dashed here, so we end up with our matrix being given by 0, 1, 1, 0. Now an alternative to doing it with a diagram such as that is simply to consider the effect on the unit vectors I and j. So starting off with I and j like this, we can see that A will do that reflection in the x-axis. So A being the reflection produces the following, where this is I dashed and this is j dashed. So that's the reflection in the x-axis, We then do a rotation of that one, B, and we end up with J double dash, we could call it, because it's been transformed twice at that position, and I double dashed here. And so the combined effect of A followed by B is given by the matrix for these unit vectors. So again, we can see that I double dashed is at 0, 1 and J double dash is at 1, 0. So whichever way you prefer to look at the combined transformations. Now what I want to do now is to consider, well, can we get that directly from the matrices for A and B? So let's look at the products. Well, A, B, if we consider the matrices in that order, remember we can write these with square brackets if we wish. So 1, 0, 0, negative 1 is A, and B is 0, 1, negative 1, 0. And if you multiply those two together, A followed by B, in other words the product A, sorry, not A followed by B, in that order, the matrices written in that order, A, B, we get the following product, which is given by 0, negative 1, negative 1 and 0. Whereas if we do the product in the other order, B, A, then we get them written like this. B is given by this matrix, and A given by this one, and that gives us the desired result that we want, which is 0, 1 and 1, 0. So the transformation A followed by B, the correct matrix product for that is BA. So in general, if we have a transformation, transformations M and N, NM is transformation M followed by N. Whereas if we do it in the other order of the product, MN is transformation N followed by transformation M. This is very similar to functions that you would have met in another context. And if you think about it as in a diagram, if we go from a vector xy, we first of all need to transform that by M in the top one, so that would give us M times xy, and then we need to transform that by N, so we get NM times xy. So this product here, NM, is the top one. It's transformation M followed by transformation N. So here's a typical question from an exam. It says find the matrix S that represents a stretch of scale factor 3 in the y direction, followed by an anti-clockwise rotation about the origin. Well, again, I'll do this in two different ways. One using the matrix multiplication. So the matrix S is the stretch scale factor 3 followed by the rotation. So if I call the stretch P and the rotation R, the matrix for P, which is a scale factor 3 in the y direction, is 1, 0, 0, 3, and the matrix for R, which is the positive 90-degree rotation, is given by 0, 1, negative 1, 0. Now if I want to do P followed by R, then to get S I have to do the product, which is RP. So that's first P and second R. So therefore it's given by 0, negative 1, 1, 0 multiplied by 1, 0, 0, 3. And that, if you do the multiplication for that, we get 0, negative 3, and then 1 and 0. So that's the matrix S. An alternative to that would be to consider our unit vectors I and j. So, well, what happens if we do the stretch scale factor 3 in the y direction? So this is P, which is the stretch in the y direction, which produces this, where this is 3 and this is 1. So this is j double dashed, sorry, I beg your pardon, j dashed, and this is I dashed. And then we follow that by an anti-clockwise rotation of 90 degrees, which is followed by R, and so we end up with I dashed being up here, or I double dashed being here, and j double dashed in that position. So again, you can see that j double dashed is the vector negative 3, 0, and I double dashed is the vector 0, 1. Well, that's the end of that video. In the next one, it's 2.5, matrices 2.5, we'll consider transformations in 3 dimensions.